Is by Professor Raymond Mooney, and I see him already. Hello, yeah. So I'll introduce him briefly and then the talk can start. So Raymond J. Mooney is a professor in the Department of Computer Science at the University of Texas at Austin. He received his Ph.D. in 1988 from UIUC. He is an author of over 180 published research papers, primarily in the areas of machine learning and natural language processing. He was the president of the International Machine Learning Society from 2008 to 2011. He is a fellow of AAAI, ACM, and ACL, and the recipient of the Classic Paper Award from AAAI 19 and Best Paper Awards from AAAI 96, KDD 2004, ICML 2005, and ACL 2007. So today he is going to talk about deep learning for automating software documentation maintenance. So welcome, and it's a great pleasure to have you here.
Okay, can you hear me okay?
Yes, we can hear you.
Okay, well, let me try to share my screen. Can you see that okay?
Yes.
Yes.
Does that look good?
Yeah.
Yes, all fine.
And it's
Good to
switching
go.
okay?
Yes.
Yeah.
Okay.
So over to you.
Okay, great. I think we're ready then. So I appreciate the invitation, and I'm glad to be here. Yeah, so I'd like to talk about some of our recent work on deep learning for automating software documentation. And this joint work primarily with my PhD student, Sheena Pantaplakal, but also some other colleagues of mine here at the University of Texas at Austin, Peng Yu, Milos, and Jesse. So I picked this partly because of the theme of AI for data and data for AI. I thought this work was maybe a little bit relevant to that topic. And the idea is there's been a fair bit of recent work on trying to treat open source software repositories as an interesting source of data and trying to apply machine learning to that to try to productively help the development of software by training on large bodies of open source software like you can get from GitHub. And learning all sorts of interesting things about software by mining that publicly available open source code. And people have tried applying a variety of statistical and neural language modeling techniques to code to support a variety of tasks, such as auto code completion, where you can figure out what you're going to type for the rest of your program, programming by voice, where you just want to talk about your program and get it. And then by using the language model to sort of know what normal code looks like, that something might be abnormal and might actually be a bug, is actually to use these large language models trained on open source software to do bug detection and repair. What I've been particularly interested in is trying to use open source software to learn a connection between code and natural language by mining large repositories of open source software that have both natural language commentary and code. And there's a variety of tasks you can look at in that context. One is language to code, where you learn, like for semantic parsing, to be able to map natural language directly into executable software. The other is to flip it around or do code to language, where you learn to generate natural language that's descriptive of code, to like generate comments automatically. Or a task I'll particularly talk about today is updating comments to account for code changes. And then code retrieval. How do we actually retrieve code using natural language queries? And by learning models that connect language and code from large bodies of open source software, I think you can learn to support all of these tasks. So initially, my work in this space was in the language to code space. I've actually been working on this problem of learning semantic parsers that map natural language sentences to formal executable representations, such as database queries. I've literally been working on that for decades, starting back in 1996 up until maybe a decade ago, when I sort of got out of that area. And I've always defined semantic parsing as machine translation from human language to computer language. When I was on sabbatical at Microsoft Research 7 years ago now, I worked with Chris Quirk on this problem of directly of language to code, where we tried to map natural language descriptions to these scripts that were available on a site called If This Then That, or IFTTT. And we tried to mine the data on that site to automatically learn to map natural language to small little sort of script for your smart devices. These are a couple of my favorite examples from that. Flash my Philips Hue light bulbs red and blue when the Cubs hit a home run. Or this other one, remind me to drink water if I've been at a bar for more than 2 hours. So we tried to take that language and map it to actual executable code by training on data that was available on this IFTTT site. Just one last thing in this space of language to code is this idea of dialogue for language to code. Due to ambiguities and people not being precise about what they really want in their initial specification, it might be hard to map language to code in a single shot. And we might want to go engage in a back and forth clarification dialogue where, I initially say what I want, and then the system says, well, what about this case, and resolve this ambiguity and get clarification and go back and forth until it eventually has enough information to write the code that you want. And we applied this to this If This Then That site, and here's a sample little dialogue, and that was a paper back at ICML-05 back in 2017. So I've historically worked a lot on language to code, but more recently that I want to talk about today is our work on going the other direction of code to language. In particular, doing code to language for automating comment maintenance. So we had a paper at ACL last year on learning to update natural language comments based on code changes that I'd like to talk a little bit about. And then earlier this year at AAAI, we had a paper on a related problem of what we call just-in-time inconsistency detection between comments and code. And that's at AAAI this last year. So if you're interested, you can get more details in those two papers. The idea is that code is constantly evolving and changing. And a lot of times people change their code and forget to update their comments. And that can lead to all sorts of confusion and bugs. So in this case, you have an example here. We have some get score method, and say someone replaces the max in this expression here with a min, but they forget to update the comment that they should now change this highest to lowest. That can cause all sorts of confusion. So we wanted to look at this problem of how can we use all the data on open source repositories to train a model that can learn to update your comments when you change your code. So the idea is, maybe here we have this piece of code and we've added this to map this angle here into degrees. We want to know that, oh, we need to change the comment to add in degrees to the comment. So the idea is that we start with some old piece of code and an old comment that describes it. We get a new updated version of the code, and we want to predict the new updated comment from that to maintain consistency. And so we particularly propose approaching this with an edit model. Rather than trying to generate the new comment completely, we just want to learn sort of a sequence of edit commands that will change the old comment into the new comment to properly get it to coincide with the new code. When developers edit comments, they don't delete the old comment and write a whole new one from scratch. They just go in and slightly edit the old comment to update it to do the changes that adapt to the code. And we're trying to do the same thing. So we want to take, you learn to edit the old comment into the new comment rather than to just generate the new comment from scratch. We want to implicitly learn those edits by directly generating the new comment. If we tried to just generate the new comment using the old comment as context, we could just build a model that just takes the old comment in and the old code and the new code and just generates the new comment from scratch. You'd have to learn to copy a lot from the old comment in order to do that. We'd rather define actually an edit sequence where it learns to explicitly know what edit changes to make. And we believe that's a better way to learn to automatically change the comment to update it to be consistent with the code. So we have this example here where we replaced the max with a min, and we need to learn what we need to do is we need to edit this highest comment word to change it to the lowest comment word. So we want to address that with an edit model where we learn sort of a sequence of edit commands, and we put together a particular edit command sequence, but you could imagine various variety. But this is just replace the old word highest with the new word lowest is the sort of edit sequence we want to predict to update that comment. And what we're going to give it as input is an edit sequence that encodes the changes that happen to the code. So with that, we replace this max with a min. So we get an edit sequence that defines what happened to the change in the code, and we want to predict an edit sequence about how we should edit the comment to update it appropriately. So the details of the model we use to do this are in the paper. We tried also transformer type models, but we actually found we got better results on this with a more older fashioned RNN model, particularly a bidirectional gated recurrent unit, a bi-GRU sort of model. So we take the edit sequence for the code, and we put that through a bi-GRU encoder, and we take the old comment and encode it using a bi-GRU, and then we give both of those embeddings to a decoder that learns to decode an edit sequence about how the comment should be edited to update it to be consistent with the new version of the code. And we found that, well, that just looks at things sort of locally. So we found it a little bit useful to do a beam search and generate multiple possible edits, and then generate the actual final edited code, and then re-rank the final edited code based on a re-ranking function that I'll talk briefly about. So the overall architecture uses, some RNN technology to encode the edit sequence from the code and the original comment, and tries to predict and edit multiple edit sequences for the comments, and then searches through a sequence of those using beam search to get several options, and then re-rank the final options to get the final best one. And particularly to give the final re-ranker some global information, we wanted to incorporate 3 pieces of information. We want to accurately update the old comment with minimal modifications. And to do that, we just, in the re-ranker, we use a metric that just looks at meteor, a classic MT metric that looks at, well, how similar is the old comment to the new comment? Because we don't want to change the comment unnecessarily. So being closer to the old comment, given everything else, would be better. But we also want the comment to be suitable for the new method and conform to whether their comment styles are appropriate for the project. So we also just build a generation model using a similar sort of RNN generation approach, seek-to-seek sort of approach, to generate the new comment just given the new version of the code. And we look at how likely that code that's generated from the edit sequence is given that model. And we do a final re-ranking that takes into account the beam score here is the original score from the original model, and then it takes into account the similarity to the old comment, and also how likely would you just generate that comment to be consistent with that new version of the code. And we set these hyperparameters based on validation data and re-rank to get the best final candidate for the new version of the comment. Okay, so we ran a bunch of experiments on data that we mined from GitHub. So how we did this was we looked at a bunch of projects on GitHub. I guess it lists here like 526 different projects on GitHub. And we looked at the sequence of commit histories. And we tried to find a sequence of 2 commits where both the comment and the code were changed from one commit to the next, so that we can learn a model of how to change a comment when you change the code from that data. So you're mining simultaneous updates to the comment code methods from consecutive commits. Now here where it gives some little bit of data on that we collected, like 5,700 some training examples from 500 some projects, and then we also tested on completely separate projects. So this is sort of a cross project to show generalization across project. We tested on a completely different set of 281 projects from which we mined 736 examples of comment update. Okay, so we compared our edit model to a couple of baselines. One that actually can work surprisingly well, because a lot of times when you're changing the code a little bit, you don't really need to update the comment that much. You can actually do pretty well by just copying the old comment. So it just says, let the new comment be the old comment. Or you can just say, let me generate a new comment from scratch from the new method using a standard seek-to-seek RNN sort of generation model. But we also applied the same sort of re-rank beam search and re-ranking that we applied to our model to be fair on that. And then we also found that a lot of times they're pretty simple changes, like people will just change the output type. And also sometimes they'll add this thing where it's like, if the input is null, then output is null. So we came up with sort of just a hand-based template that actually works surprisingly well, as you'll see, but it's sort of a rule-based, sort of manually constructed baseline. And then we evaluated the new comments for the test cases in several ways. One is exact match. Did it produce something that exactly matched the new comment that the developers of the original code did when they changed the code in that way? A couple of other just generic generation metrics from MT that you can use to compare the old comment to the new comment to the gold standard comment from the data. And also a couple of metrics that have been developed that specifically look at edits that show how well you're doing at editing one string into another string. Despite being trained on more data, the generation model that just tries to generate the comment from scratch is doing actually quite poorly. So you clearly want to exploit the existing comment and learn to update it. Even the simple dumb rule-based model does significantly better than the generating from scratch model. But our edit model does the best, particularly if you look at these edit metrics. It shows how well it's actually editing the new comment into the old comment into the new comment. So these, I think, are automated metrics that sort of show that the model is learning to update the comment reasonably well. But I really think there's no substitution in a task like this for actual human evaluation. These automated metrics have all sorts of issues with them. So we did a smaller scale, but I think a pretty rigorous human evaluation, where we gave a bunch of subjects, and to do human eval in this space, you need to find experts. So we had 10 participants with at least 2 years of Java experience. All our code, I think I mentioned, was, if I didn't, we all do Java code from GitHub on this. And we give them up to 3 suggestions. One is the generation model from scratch. One is this rule-based baseline, and the other one is our edit model. But we also give them the option of selecting none. So we should have showed them, hey, here's the old code and the new code. Here's the old comment. So we show the human software engineer all those things, and we say, pick amongst these options, what is the best updated comment? But they can also select none if they think all of them are bad, or that the old comment really doesn't even need to be updated. We had each participant annotate about 50 examples. Each example was by 2 annotators, so we could look at cross-annotator agreement. And so here's some of the results. First, I'll just mention this Krippendorf alpha. We did get pretty good agreement between the two judges. So this is something that a reasonable software engineer can judge, is which one is a better updated comment. And the generation from scratch model does pretty poorly. The rule-based model a little bit better, and our edit model does the best. But there are a lot of cases where the software engineer is actually picking that none of those updated comments are really the best. And a lot of those cases are actually a case where the comment really didn't need to be updated, even though the data we collected was all collected under the restriction that the comment and the code were both updated. But sometimes people just make polishing changes to the comment, even though it doesn't really change the semantics to match the change in the code. So that led us to the next part of the project, which is all that data we collected assumed that when you updated the code, you needed to change the comment. But a lot of times when you update code, you don't actually need to change the comment. It doesn't affect the comment. So we had to look at this problem of code comment inconsistency. And this is a problem that other people have looked at in the past. Is can we just learn a model that learns whether a particular comment is consistent with the code? And one way to do this is just to do what we call ad hoc tests, which is I just look at comment and code and see if they're consistent. But we also try to do this in what we call just-in-time comment code inconsistency detection, where we check when someone changes the code, does that change to the code require a change in the current comment? So this post-hoc inconsistency detection is just, I'm given comment with code and I want to say, is it inconsistent or not? So in this case, it's getting that says the highest value, but it's actually getting the min. So we would say that comment is not consistent with the code, versus over here where it says highest and it's doing the max, that is consistent. But what we really want to do is do this in a real-time sort of just-in-time setting where we just saw the person change that max to a min. Now we want to know, does that make the comment that we had before about highest value consistent or not with the data? And so we want to check when the change is made to the code, does that render it inconsistent with the comment? And that's what we call just-in-time inconsistency detection. So the idea is, we have comment and we have code. So the post hoc approach is I give comment, I give code. Are they consistent? But the just-in-time is, I just changed the code from min to max here. Does that now render the comment inconsistent? So just in time, when they make the change to the code, I recognize that I've now created an inconsistency between the comment and the code. So we tried to build a deep learning system that learns when you change code, does that render the code inconsistent with the comment? So we take the existing comment and encode that with a GRU, a bidirectional GRU. And we do some self-attention over that, so it starts to look a little bit more like a transformer. And then we also encode the changes to the code. And the details of this are in the paper. But we tried several ways of encoding the code changes. One is just looking at the sequence and using a biGRU. The other is there's been a variety of work in the area of applying deep learning to code that tries to use the syntactic structure of code by looking at the AST, the abstract syntax tree for the code. But we also developed a model that looks at how the AST was edited, sort of the change to the tree structure of the syntax of the code, to see if that was better. And we used a gated recurrent neural network, a gated neural, so that's the GGNN is graph gated neural network to do that. And then it does cross attention between the code and the comment, and then puts it through a couple of continuous fully connected layers to make a prediction. Did that change to the code render that comment inconsistent with the code? And we try to train a model to learn when changes to code renders that code inconsistent with the current comment. So again, we went into GitHub and collected a variety of data for training this model, where we look at a commit history where both the comment is changed and maybe the code is changed. The code is changed, but maybe the comment is changed or not. In the case where the comment has changed, then we say, well, if the person changed the comment when they updated the code, then that probably meant that the existing comment was inconsistent. Now that can be a little bit noisy because, like I said, a lot of times people will change the comment where they'll just like maybe clean up a typo in the comment that they happen to notice when they change the code, but it actually wasn't the case that that change rendered that old comment semantically inconsistent. So there's a little bit of noise in this data, and I'll mention that we did some cleanup on that later. But if they change the code and they didn't change the comment, so the new comment is the same as the old comment, then that's sort of an indication that the comment was already consistent with the code. Again, that could be mistaken too, because our whole point of using this technology is sometimes people are stupid and they don't update their comment when they should. But we're assuming that that's negative. So this can be some noisy data, but it is at least a reasonable set of data to train a model to detect comment code inconsistency when it's created when someone changes the code. So there's a little bit of statistics on the data set we created. We made a pretty big data set of 800 and some projects and got some, 32,000 training examples. And then we have like not quite 4,000 in the test case. And we looked at particular types of comments for Java programs, at return comments, parameter comments, what are called summary comments, which is like the first sentence in the block comment before a method. But like I said, some of this data is pretty noisy because assuming this means this is consistent and this means it's inconsistent are not necessarily always true. So we created what we call a cleaned up data set where we manually looked at it and made sure that the consistent and inconsistent labels were correct for a small sample of 300 examples. And then the results show are the results on the cleaned up test data, and then the normal test data that might be a little bit noisy because of the assumptions we're making about how people are updating their comments in code. So there was a prior piece of work that tried to do just-in-time comment code inconsistency detection that was not using deep learning, that used a random forest approach with a bunch of engineered features. So they didn't actually use any actual use of the comment language or the code. They engineered some features. And so this is a baseline. Their system does reasonably well on our data set. In fact, it does better than just trying to do post-hoc using a sequence model where you try to detect, is this code inconsistent with comment without taking into account the changes to the comment, to the code versus the old comment. But our edit approach does a little bit better. Our just-in-time, sequence-based deep learning approach. But we also looked at using the syntax graph of the code changes, as I said, using the abstract syntax tree. And then also this hybrid combines both the graph representation, the syntax tree representations with the sequence representation, and that does a little bit better all that, where that wasn't statistically significant. But this manually engineered approach did use some pretty interesting manually constructed features. And so we also added some of our own manually constructed features to these sequence and graph representations and boosted the performance a little bit more. So at the end, we're getting up to in the high 80s, at least on the cleaned up data, and in the low 80s on the not cleaned data that might have noise in it. Okay, so incorporating these existing manually constructed features gave us the best performance overall. Okay, so our paper at AAAI earlier this year then shows results on combining these two, because the idea is to use this in practice. Then you'd first you'd see a change to the code. You'd first have to run our consistency detector to check whether that change in the code renders it inconsistent with the current comment. And if you decide that that change does render the existing comment inconsistent, then you want to go ahead and generate a new updated comment. And the paper, we show combining these two processes together to do both consistency detection, and if it's inconsistent, then do the update, and then do both automated and human eval for that case. You can see the paper for the details on that. Okay, so I want to leave plenty of time for questions, so I'll try to wrap up here and spend a little bit of time here talking about future work. So maybe I wasn't completely clear that the existing work that I've presented here is all on method comments, where the comments describing the method, sometimes the return comments, sometimes the parameter comments, and sometimes just the block comments for the method. But it'd be interesting to look at other types of commenting codes, like comments at the level of an entire class, or inline comments. We just look at method level comments. We don't look at higher level, class level comments, or sort of immediate inline comments. Also, all of the results I've presented today are in Java. Of course, it'd be good to test these sorts of comment update and consistency detection methods on other programming languages. Another thing we've thought about and started to do some work on, and the results were a little bit disappointing, we're trying to use, this thing only looks at the current method and tries to decide all these things. But maybe if I looked at an abstraction of that method in a higher level abstract class in the object-oriented hierarchy, that could provide me some interesting context. Or what if I looked at the methods that called this method, or the methods that this method calls? So we're calling that either the class abstraction hierarchy or the calling hierarchy. How could we add more context to understand this method better by understanding where it lies in the calling hierarchy and the class abstraction hierarchy, and use that information to improve comment generation and comment update? Then, of course, it would be nice to take all of these and actually put them into an interactive development environment where people, as they're changing their code, it maybe pops up this little window. Oh, I just noticed you changed your code. You might want to change the comment in this way, and then give them a nice tool for like accepting that change to the comment or editing it. So actually integrate these tools into an actual software development environment, and then do an actual user study, where we allow users to use these tools and see if that leads to them actually developing more effective software, where the comments and the documentation is better maintained by using these deep learned tools that have been trained on all this available open source software. So I've assumed that when we find a comment code inconsistency, that means that, oh, the comment needs to be updated. But maybe it means that actually there's a bug in the code. So maybe comment code inconsistency doesn't mean that the comment is wrong. Maybe it means that the code is wrong. And how can we use this ability to detect comment code inconsistency to maybe detect bugs and decide that, ooh, maybe this is a problem with the code and not a problem with the comment? Another idea that we've talked about is this all tries to either generate the comment from the existing comment in the method, or generate it from scratch. But what about, a lot of times I might find code somewhere else in some other repository, and then take the comment from there and try to learn to edit it. So maybe I can find a similar method somewhere in some software library somewhere, look at the comment for it, and then just learn to update the generated comment for this new method based on editing a comment for a similar method in some repository somewhere. So I can use this edit model to actually learn to generate comments by retrieving comments for other previously developed code that's similar and edited it to adapt it to the current code. And the thing we've been looking at most recently that we have some initial results on that I don't have time to talk about is there's been a lot of work on language encode, but not with dialogue. So we've been looking at GitHub issues. I don't know how many are familiar with that, where they're actually discussions between developers about the open source software, maybe like a bug fix, somebody reports a bug, and then the developers engage in this dialogue on this GitHub issues tool to debate what the problem is and how to fix it. And we've been analyzing these dialogues and trying to learn a model that can learn to suggest like bug fixes based on the discussion between the developers. So you sort of have a bot that sort of contributes to the software development dialogue, say about a bug report, by having trained on all these other dialogues about all these other software issues that have been out there on GitHub. So it trains on a bunch of GitHub issue data to try to learn an agent that can engage in an intelligent dialogue about software. Okay, so I'll wrap up there to leave plenty of time for question, even given the fact that we started a little bit late. So I think deep learning applied to software repositories offers many opportunities to develop tools for improving software development, particularly in learning to connect natural language to code. In particular, we've developed these sort of just-in-time methods that every time you make a change to your code, it figures out whether that change to the code renders it inconsistent with the existing comment. And if it does, can suggest an updated comment that will restore consistency and train a nice deep learning model to do this based on all this available nice data that's now out there on open source software. And we've gathered some, I think, reasonable extensive experimental results on a reasonably sized corpus based on Java code from GitHub that tries to demonstrate that these deep learning techniques really can learn to do these sorts of documentation maintenance tasks reasonably well. Okay, I'll stop there.
So thanks. Hello. Yeah, thanks for the wonderful talk. Yeah, so I do see a couple of questions. You can see a Q&A window below. Maybe if you can click on it, you can read them also, or I can read them out also.
Yeah, so a slightly bigger question is, is there any specific...
okay, that's the chat. Can you see the Q&A, which is kind of beside it?
Oh, sorry. Oh, okay. Yeah, I got it. Is it highly dependent on modification made? For example, max was changed to min, then the system should have the definition of max and min. But if the definition of the change is not clear, function call A0 was changed to B0. Well, I mean, it would have to learn, you know, from the, I mean, it does use the language in the names of the functions. And so it would have to, you know, maybe it is a system, a user-defined function. But, you know, if that user-defined function has some reasonable English name to it, it could still exploit that. So we do what's usually, when people do this, they usually what's called subtokenization, which is you break like names of methods and variables based on case, or based on the camel case or the snake case into individual tokens. And hopefully those are actually English words that the model of the code could learn. So it doesn't, and even min and max, it has to learn that from the code, what min and max mean, and that min means whatever lowest and max means highest. So as long as it could break apart the name of the user-defined function into meaningful terms that it can maybe relate to the English words in the comment, it could still hopefully learn to do that even for non-system calls, if I'm understanding the question. Does that answer? I guess. So, but they don't have access to the speech, right? Okay. Hopefully that's okay. Your take on CodeX. Okay, so yeah, so you know, CodeX is, of course, made a big splash out of OpenAI in terms of they process on a lot of different code. So you know, so they train on both the language and the code, and in some sense can complete on both. But I mean, it'd be interesting to apply that directly to this model for updating comments. But I mean, it's not specifically designed to do these specific tasks that I outlined. It'd more have to be where it was starting from scratch, like the start from scratch model. So it's really not going to be able to use the sort of existing content and the sort of edit capability that our model does. So I agree that, when we did this work, that was actually before CodeX came out, but it would be interesting to apply it to our data. But I think it's going to end up more in the space of the generate from scratch model, because it's not really learning an edit model of any sort, which I really think is a powerful tool in these cases of updating comments. How does the model behave as code gets more complex or larger in size? I mean, I guess we trained on a lot of real projects from GitHub. I think that's an interesting question. We could have looked at when it's making mistakes. I mean, maybe it's like for longer methods or something. We could have looked at how its errors correlate with certain properties of the code that it's I don't have any quantitative data on this. This is where it'd be better to have Sheena here because she has more experience with the actual data. But I think, not surprisingly, I think she did tell me that when there are a lot of changes to the code, that's when it has problems, right? That when there are just a few changes to the code, it's pretty good at finding the few changes to the comment to update that. But if there are huge amounts of changes to the code, not surprisingly, the system starts to fall apart. So I'm pretty sure that, yeah, certainly the bigger the changes are to the code, of course, the more complex the change might need to be to the comment. And of course, in those cases, the model is not doing as well. Okay, so that's all I'm seeing.
I had just one small query. So just continuing on the point that you said, like if the changes are really big, then do you think it makes more sense to generate a comment from scratch?
That's a very good point, and I absolutely agree. So maybe at some point you need to learn that the edit model is not appropriate, that this code has changed so much that I would be better off generating the comment from scratch rather than trying to edit the old comment. So that's a very good point, and I think you would want to learn a model then to then predict when you should flip and say, ooh, this is just too many changes to the code. Maybe it's just as simple as the number of code token changes or something. It'd be interesting to check, but maybe it's just a simple threshold on the number of code token changes, which should switch you from an edit model to a generate from scratch model. But that's a very good point. It'd be interesting to look at that. Thanks.
Okay, so one of the organizers, Animesh, has a question. So yeah, Animesh.
Hi, Ray. Animesh here. So I was wondering, like when you were showing this generation of the comments, like are you also thinking in future to incorporate ideas like explainability, because that might like resolve to some extent the problem that many of the software engineers were finding, that no code, no comment changes at all required. So if the model could be made a bit more explainable as to why the model is feeling that some comment needs to be changed or some new comment needs to be generated, that might that could probably help. So what would be your take on that?
Yeah, no, that's a very good question. I have actually worked on explainable AI. I was involved in the DARPA explainable AI project, but you're catching me between projects, because I've done explainable AI more on grounded language, more of the sort of stuff that my friend Mohit talked about, where VQA. We've actually done a lot of explainability work on VQA. I've not done explainability for this code work, which I think would be very interesting. I think what you would want to collect in that case, which would be hard, is human rationales, because you need some data to train a rationale model. And so you would need, and that's not, you can't just scrape that from GitHub, right? You would have to actually ask software engineers, okay, why did this code change require this change to the comment? If you could get that sort of data, I think you could train a rationale model that could learn to, provide those sort of rationales. The problem would be, where the hell would you get that training data? Because that's, with all the data we've gotten so far, we just naturally scrape from what's out there on GitHub. But that people don't provide rationales for their changes when they make these changes on GitHub. Well, you could go look at the commit message. Maybe the commit message might provide some additional information on that. So it'd be interesting to see to what extent. Commit messages are sort of notoriously bad, though. People do not do a good job. If people put in really detailed rationales about why they made the changes they did in the commit message, then maybe, but I wouldn't be hopeful that sort of rationales are available even in commit messages. But in general, I like that idea.
Yeah, so I think like we had a parallel project where we were doing the same thing with hate speech, but there it was a bit easier to get the rationals because you could, you could resort on AMT workers to do it. But I think in this case, like it might be too much to rely on AMT workers to have these rationals tagged. I'm not sure, like, but like, say, first year or second year programming students, like, if they're given code snippets and the comment messages, like, it might be worth checking, like, whether that kind of an annotation framework makes sense or not. Thank you.
Yeah, so I like, there's another question that did come up in the QA. It says, could a machine learning model be used to detect a region of code so complex that it needs a comment? So there is someone, I don't have the site for this, but there is someone who looked at when should I put an inline comment somewhere. Actually, it was Charles Sutton. Charles Sutton, if anyone knows him, he's done a lot of work in this language and code space and just machine learning for code. But he looked at this problem of learning when you should put an inline comment, that this particular line of code is sort of opaque and you really should add an inline comment. I think that's a really cool task of where should I put inline comments? So there, I know Charles Sutton has a paper on this for the person who asked that. But it's another really interesting problem in the whole comment and code space. Like I said, I mentioned inline comments in my future work session. There hasn't been a lot of work on inline comments.
Great.
Okay.
Yeah, thanks for answering all the questions.
Okay, well, thank you for the
yeah,
invitation.
and thanks again for that wonderful talk.